Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about integration by partial fractions when you have non-repeated quadratic factors. In the last two videos, I introduced the technique of using partial fractions to do integration. And in both of those videos, we had linear factors in the denominator of our rational function. They may have been non-repeated like here, or repeated, for example, if there was a power on one of those factors. In this video, I want to talk about how we use partial fractions to integrate rational functions, where we may have linear factors, but we also have quadratic factors. So x is simply a linear factor. X squared plus 4 is a quadratic factor. So let's take a look at how we do that with this example. When you first see the question and you're asked to integrate a rational function, you always look to see if any of your other patterns of integration will work first. In this case, they don't. Then the next step you're going to do is you're going to look at the degree of the numerator and the degree of the denominator. If the degree of the numerator is greater than the denominator, then always do algebraic division to begin with and break it down. In this case, the degree of the numerator is less than the degree of the denominator. So our next step is to factor our denominator. We don't factor the numerator. We can factor an x out of each term. Like I mentioned, this is a linear factor. This is a quadratic factor. Now we're just going to break this fraction down into its partial fractions in a similar manner as what we did with linear factors. So in order to do that, we take a look at the factors in our denominator. Our linear factor is x, therefore our numerator is some constant. We don't know its value, we'll call it a. The second fraction will have a denominator of the other factor, x squared plus 4. Because this is quadratic, we have to allow for a linear factor or expression in the numerator, and the way that we're going to express that is bx plus c. We don't know the values of a, b, and c, but we can find those by multiplying both sides of the equation by our lowest common denominator. When we multiply the left-hand side, both factors cancel, and we're left with 4x plus 4. When we multiply the right-hand side, we do it each term at a time. So when we multiply that, the x cancels and we're left with a times x squared plus 4. And when we multiply this fraction by our lowest common denominator, the x squared plus 4 factor cancels, and we're left with bx plus c times x. The way that I'm going to solve for a, b, and c is going to be a little bit different than I did in the previous examples because we can't use that previous method for this. So what I want to do is expand on the right-hand side, and then I want to group the x squared terms, then the x term, then my constant. So ax squared plus bx squared, I'll factor out an x squared, and I'll have a plus b as my coefficient. I have cx as my x term, and then I have 4a as my constant term. Now we're going to take a look at the left-hand side. I don't have an x squared term here, therefore the coefficient would be a 0. Now, I know that a plus b has to equal 0. I know that c has to equal 4. And I know that 4a has to equal 4. So the x squared coefficients have to equal, the x coefficients have to equal, and the constants have to equal. So 4a has to equal 4. So we've already got a value of c. Here's our value of a. A is equal to 1. Then I plug that into equation 1. 1 plus b is equal to 0. Therefore, b is equal to -1. So putting those values in for a, b, and c, we get our partial fractions. Now we're going to do the integration. Let's break up each of the terms. So this is going to equal integral of 1 over x dx plus, if we take a look at this function, We don't have a technique, any of our other techniques of integration to deal with that. So what I want to do is I want to break up the numerator. So I'm going to get the integral of negative x over x squared plus 4 and the integral of 4 over x squared plus 4. So I simply broke this fraction up into these two fractions. If I add them together, I would get this back. Now let's move this negative sign out front of the integral sign. And let's move this 4 outside the integral sign. We can do that with coefficients. And now we're going to take a look at what patterns can be used to integrate each of these. I now have functions that I can integrate according to our previous patterns of integration. So the first pattern of integration that we want to use is our basic log form, which says the integral of 1 over u du is the natural log of the absolute value of u. So if we take a look, that applies to this example. So this integral will be the natural log of the absolute value of x minus. Now let's take a look at this example. We can use the same pattern where u is x squared plus 4. Therefore, du will be 2x dx. I have the x part, which is the most important part. I just need to introduce a coefficient of 2. And as long as I balance that with a coefficient of 1/2 outside, so I haven't changed the value, I can now integrate this. So it will be 1/2. I have 1 over u du, so it'll be the natural log of u. Now in this case, I could put the absolute value signs, or I don't actually need to, because x squared will always be positive, and adding 4 to a positive number will still be positive. So you may or may not see the absolute value signs in a situation like that. Our last term now can be integrated using our inverse tan pattern of integration. If we have the integral of 1 over u squared plus a squared du, here's our integral. If we take a look at this, we have 1 over, this could be our u squared, so u squared is equal to x squared, in which case u is x, therefore du is dx, and plus a squared, so a squared is 4, therefore a is 2. And we have everything the way we need it to do the integration, so let's plug it in. Our integral will be 1 over a, don't forget about this 4, so 4 times 1 over a, 1 over 2, times the inverse tan of u, which is x, over a, which is 2. I would probably clean up 4 times 1/2, write that as 2, and then I would probably combine my two log terms using my properties of logs, and I'll show you what that would look like. So first of all, I can deal with this coefficient using my third property of logs, move it into the exponent position. Then I can combine these two terms through division, combining into one log term. So my final answer would be natural log of the absolute value of x divided by the square root, or x squared plus 4 to the 1/2, plus 2 times inverse tan of x over 2 plus c. So you probably would see the final answer written like that. This is also correct. It depends on whatever is preferred. Let's take a look at another example. In this next example, the degree of the numerator is 3. If I were to multiply this out, we could easily see that the degree of the denominator is 4. Therefore, we leave it like this. We don't do any algebraic division because the degree of the denominator is higher. Then we look to see if we can further factor. This is unable to be factored, so those are our factors in our denominator. We have a linear factor of x, which is repeated, and then I have this as my quadratic factor. So first of all, I want to break this up into its partial fractions before I worry about integration. In order to do that, I take my first factor, linear factor of x. My numerator is going to be a constant, which we don't know, we'll call a. My next denominator, or my next fraction, will have a denominator of x squared. So it's a linear factor repeated, so my numerator is b. My last fraction will have this quadratic function as the denominator. So because it's quadratic, my numerator will be linear. It will be cx plus d. So my first step is to try to find what a, b, c, and d are. And in order to do that, I multiply both sides of the equation by the lowest common denominator, which is this. I don't really have room to show it, so hopefully you can follow along. When I multiply the left-hand side by this, the denominator cancels totally. and I have x cubed plus 3x squared plus 2x plus 4. When I multiply this term by my lowest common denominator, one of the x's cancels, so I'm left with a times x squared plus 2x plus 2. Similarly, when I multiply this term by it, the x squareds cancel, so I'm left with b times x squared plus 2x plus 2. And when I multiply my last term by it, this whole thing will cancel, and I'm left with cx plus d times a factor of x squared. My next step then is to expand everything on the right-hand side. Once it's expanded, now I want to combine all my x cubed terms. So I have ax cubed plus cx cubed. I'll factor out the x cubed, and I'll have a plus c. Then my x squared terms. I'll factor out the x squared, and I'll have 2a plus b plus d, x squared. Then combine my x terms, which is this and this. Factoring out the x, I have 2a plus 2b times x, plus my last term, which is my constant term. Now I'm going to get 4 equations with my 4 unknowns using these coefficients. My first equation is this coefficient for my x cubed term has to equal 1. So a plus c has to equal 1. My next equation, my coefficient for x squared is 3. So 2a plus b plus d has to equal 3. My third equation, 2a plus 2b has to equal 2. Let's just simplify that. Let's divide both sides by 2. So in other words, a plus b has to equal 1. It's a little bit easier. You don't have to. And then lastly, my fourth equation, my constant, 2b has to equal 4. In order to solve, I'm going to start with equation 4, because it says 2b is equal to 4, which allows me to solve for b. Now that I know b, let's solve for a in equation 3. So a plus b equals 1, so a plus 2 equals 1, so a is equal to negative 1. Now that I have a, I can solve for c. So a plus c is equal to 1, so negative 1 plus c is equal to 1, so c is equal to 2. And then lastly, equation 2, 2a, so that'll be negative 2, plus b, which is 2, plus d is equal to 3, therefore d is equal to 3. So I've solved for all my variables, therefore I've got my partial fractions. Let's fill those in. Now that we've done that, let's integrate. I can break this up into separate integrals. I'm going to move the negative out front, so I've got 1 over x dx. I have the integral of, I'm going to move the 2 out front, 1 over x squared dx. Now for this next fraction, I'm trying to think if I have any patterns of integration that will allow me to integrate this, and quite frankly, I don't. Take a look at this denominator and think about what the derivative of this denominator is. The derivative would be 2x plus 2. Well, I have 2x plus 3, but I could write that as 2x plus 2 plus 1. If I do that, then I can split it into 2 more fractions. So I'll have the integral of 2x plus 2 over x squared plus 2x plus 2. And that's going to be something I can integrate because I know this happens to be part of my du factor of the denominator. And then I'm left with the integral of 1 over x squared plus 2x plus 2 dx. I'm going to have to do some manipulation on that as well before I can integrate it. But right now, these 3 terms can be integrated. Following our basic log pattern, this is going to be a negative natural log of the absolute value of x. The The integral of 2 times the integral of 1 over x squared would be negative 2x to the negative 1. This follows our basic log pattern where here's our u, this whole function, and this happens to be our du. So it's going to be natural log of the absolute value of x squared plus 2x plus 2. Now, in order to integrate our last term, we're going to complete the square in the denominator. And the way that we're going to do that, if I have x squared plus 2x plus 1, that's a complete square. How did I get that? I take 2 divided by 2 to get a 1 and square it. So I'm going to write this 2 as 1 plus 1. And this is a technique I've talked about in earlier videos. Hopefully you're not lost. But this now is a perfect square. So I can write this as 1 over x plus 1 squared plus 1. Now this integral fits our inverse tan pattern. We have 1 over u squared. So u squared is x plus 1 squared. Therefore u is x plus 1 and du will be dx. A squared is equal to 1. So a is equal to 1. We're good. We can use that pattern. It fits. So we're going to use that to integrate it. The other thing I want to do is I want to write my log terms together, and I'm going to put the positive 1 first. So I have the natural log of x squared plus 2x plus 2 minus the natural log of x minus, I'm going to write that as 2 over x. Now I'm going to integrate this using this pattern. So it would be 1 over a is 1, so it'll just be a 1, times the inverse tan of u, which is x plus 1, over a, which is 1, and then I will write my constant. So we could leave our answer like that, or preferably let's combine these log terms using our properties of logs. So it would be the natural log of x squared plus 2x plus 2 over x, and we'll just put absolute value signs around the whole thing, minus 2 over x plus the inverse tan of x plus 1 plus our constant of integration. That's probably how you'll see it expressed in any kind of answers or possibly what you're expected to do. I have one more video on integration by partial fractions. The next one is going to be an example of how we deal with a function that has repeated quadratic factors in the denominator. So check it out.